Welcome back to Simplifying Synthesis, the channel where we look at complex organic chemistry and explain how it works. Last week, we started looking at the synthesis of Spirochensilide A. We covered the retrosynthesis and also the first stages of the forward synthesis, where they started with the geranyl derivative and produced the advanced intermediate. This video will be covering the remainder of the synthesis and how they finally achieved this challenging structure. Moving forward, the TMS group was first selectively deprotected using potassium tert-butoxide. This is not a common reagent for this type of deprotection, but it was necessary to ensure the selectivity due to the other silicon protecting groups present in the molecule. This deprotection is accelerated by the alpha ketone moiety, which can form an enolate, which is then protonated to restore the ketone. Following this deprotection, the alkene was then reduced using catalytic hydrogenation with hydrogen gas and palladium on carbon. This formed a single diastereomer, with the selectivity arising from the steric hindrance of the molecule, which only allows hydrogenation from one phase. As I mentioned earlier, the cyclopropyl moiety was only introduced to the synthetic strategy to accelerate the Pawson-Cand reaction. For the final product, a methyl group was needed. To convert this cyclopropyl group into the desired methyl group, the authors used a radical reduction of lithium in ammonia. Only one diastereomer was formed in this reaction, and this is due to the radical stabilization caused by the carbonyl group. This ensured that the carbon-carbon bond, which was to be broken, happened on the less hindered secondary center close to the carbonyl group, and not the undesired bond breaking at the quaternary center. Following this reduction, this alpha position then took part in an Aldol Addition. Reaction with diisopropyl ethylamine generated an enolate, which reacted with the aldehyde in the presence of di-N-butyl boron triflate to generate the target compound as a single diastereomer. The selectivity is due to the chelation control granted by the boron salt. This is able to coordinate to both the enolate oxygen and the electrophilic aldehyde oxygen and form a six-membered transition state. This is the lowest energy reacting state and therefore allows for the preferential formation of one isomer. With the new carbon-carbon bond formed, the authors then turned to the elimination of the newly produced hydroxyl group to form the enone. To complete this transformation, they use the unusual reagent of 2-fluoro-1-methylpyridinium tosylate. While typically this transformation can be carried out using simple acid or base, this reagent generated the desired E-alkene, in preference to the Z-olefin. To explain this selectivity, we must look at the orbitals of the reacting transition state. Typically, elimination reactions of this type happen through a concerted E2 mechanism, which requires an anti-periplanar relationship between the proton being removed and the leaving group, in this case, the activated oxygen moiety. If this reaction pathway was followed, an alkene with a Z geometry would have been produced. Using NOE NMR studies, this was ruled out. This type of NMR experiment utilizes the nuclear Overhauser effect and allows scientists to see what protons are close together in space. As an E2 mechanism is ruled out, we can instead hypothesize that this transformation could have occurred through an E1CB mechanism. In this reaction pathway, an enolate would first be formed by the deprotonation of the alpha proton with triethylamine, which was present in the reaction. The formation of an enolate would allow free rotation around the key carbon-carbon single bond and would allow a conformation to be adopted in which the HOMO of the enolate could overlap with the LUMO of the leaving group and eliminate the oxygen to form an E-alkene. This reacting conformation would be favoured as it minimises 1,3 allylic strain between the oxygen of the enolate group and the substituents on the carbon bearing the leaving group. The data from the NOE studies, together with this conformational analysis, allows us to propose this mechanism for the elimination. The fluoromethyl pyridinium reagent first binds to the oxygen, which increases its leaving group ability. Deprotonation of the alpha proton generates an enolate, which then eliminates the leaving group to selectively generate the double bond with an E geometry. With the enone now correctly installed, the authors then performed a conjugate addition using methyl lithium together with copper iodide to generate the Gilman reagent, which selectively adds to the beta conjugate position in preference to direct addition to the carbonyl. This reaction was stereoselective, and the authors carried out DFT studies to explain this. This computation showed that the axial methyl group, here marked with the green star, repulses the oncoming nucleophile and directs it to the opposite face of the molecule. This same methyl group influences the stereoselectivity of the next reaction, which was an alpha alkylation using methyl iodide. Deprotonation of the alpha position using potassium hydride formed an enolate nucleophile which reacted with the methyl iodide. Steric repulsion from the axial methyl group blocks the bottom face of the molecule and promotes an anti-orientation between it and the newly added methyl group. At this stage of the synthesis, the authors sought to reinstall an enone on the 5-membered ring. To do this, they used a selenoxide elimination. Reaction of the compound with LDA generated an enolate, which reacted with phenylselenyl chloride to form an alpha-selenyl intermediate. This was then oxidized with MCPBA to generate a selenoxide. This underwent a retro 3+2 cycloaddition to abstract the beta proton and generate an alpha-beta unsaturated enone, together with the elimination of selenoxide. This mechanism is similar to the Cope reaction. The next step of the synthesis was to reduce the carbonyl group to an alcohol. This was accomplished using diisobutyl aluminium hydride. The aluminium coordinates to the carbonyl oxygen, increasing its electrophilicity and allowing for the transfer of hydride to the carbonyl center, which yields a hydroxyl group upon workup. Carrying this molecule forward to the next step, the authors carried out perhaps the most interesting reaction of the entire synthesis, which was a highly selective oxidation-spiroketalization reaction sequence. The reaction uses singlet oxygen, which was generated using oxygen gas, methylene blue, and a tungsten lamp. Singlet oxygen has 2 spin-paired electrons, in comparison to the more common triplet oxygen, which is paramagnetic. This influences its reactivity and allows it to take part in cycloaddition reactions, such as this one, which is a 2+4 cycloaddition with the furan ring. This generates an interesting intermediate with a bridging ether and bridging peroxy group, together with the TBS group. This intermediate rapidly rearranges to form an oxo-alkenoic acid intermediate, together with the migration of the silyl group, and then undergoes an intramolecular ketalization reaction, similar to an acetal formation, where the carboxylate will act as a nucleophile towards the protonated ketone and will eliminate water to form an oxocarbenium intermediate. This serves as an electrophile towards the secondary alcohol present on the 5-membered ring, which can attack this electrophile in a highly selective manner due to the steric hindrance present in the ring. Overall, this sequence has formed the highly unique structure of the 5- and 6-membered rings joined by a spiroketal, all of which was accomplished in a highly selective manner to generate a single isomer. With all of the ring construction now complete, the authors turned their attention towards installing the correct oxygen groups on the rings. The TES group was deprotected using dilute TBAF. This was carried out selectively and did not deprotect the TBS group. The newly revealed hydroxyl group was then oxidized to a ketone using Des-Martin periodinane, which binds to the oxygen, increasing its electrophilicity, and allows deprotonation of the geminal hydrogen to produce the target ketone. It was a simple matter to deprotect the TBS group using HF to generate the target Spirochensilide A and complete the synthesis. Overall, this remarkably challenging molecule was synthesized in just 22 steps with a 2.2% overall yield. The highlights of this synthesis are the highly stereoselective reactions, including the semi-pinnacle rearrangement of the epoxide, the singlet oxygen-mediated spiroketalization, and the unusual tungsten catalyzed cyclopropane accelerated Poisson and Cand reaction. This is the first reported synthesis of this molecule and this unusual triterpenoid scaffold with two spirocyclic systems, and the methodology developed in this work will no doubt be applied to other syntheses. The authors have published 2 further papers detailing how this synthesis was developed, which I highly recommend reading. That's everything from this week's Simplifying Synthesis. If you like this content, please like and subscribe. I'll be back again next week, where I'll be looking at the total synthesis of O-dibenzoyl tashirone. So make sure you turn on your notifications to find out when it goes live.